using trig functions, specifically sine and cosine functions, to model real-world problems, or in other words, solve word problems using sine and cosine functions. So I've got an introductory example here. Let's just read through it. It says the depth of water at a dock varies throughout the day. Today, the high tide occurs at 4:15 a.m. With a depth of 5.2 meters. The low tide occurs at 10:27 a.m. with a depth of 2 meters. And the first part of this problem is to find a trigonometric equation, in other words, a function, that models the depth of the water t hours after midnight. So whenever you're trying to do one of these problems, you should always draw a picture. You should get a good picture of what the graph of your function looks like before you really try to work out the formula of your function. So let's draw a picture of this situation. The first thing to kind of notice is that this problem ultimately is about water going up and down. I mean, you might remember that the gravity of the moon or whatever causes the depth of water to increase and decrease throughout the day. And that's what this problem is all about. And we're trying to model the depth of the water over time. So let's try and draw a picture of what the thing should look like. So what do we know? We know that high tide occurs at 4:15 a.m. So I hope it's clear that we should be making time the horizontal axis. So let's suppose that this right here is 4:15 a.m. And at 4:15 a.m. we have high tide of 5.2 meters. High tide, that means that that's when the water is deepest, right? That's when the depth is the greatest. So I'm going to put a dot up here and say that that is 5.2. Okay, so this axis is the depth in meters. Okay, so great. The other point that I have is that I have a low tide at 10:27 with a depth of 2 meters, right? So at 10:27, let's say that that's here, 10:27 a.m., I have a depth of 2 meters. So let's say that that's down here. So this point here is on the graph. So really all I have right now are these 2 points. I know that these 2 points are on the graph. And I want you to think carefully about what the graph should look like. I find that students make the greatest number of mistakes right at this point here. They maybe assume that the graph looks like this or something. Or perhaps the graph looks like this, right? Or maybe the graph looks like this. We really have to be careful about what we think our graph looks like. This is the highest depth, and this is the lowest depth. I hope it's clear that the graph should be some trig function which looks like this, okay? Now, one thing that students often do is they sort of continue it, like they say, oh, the graph should keep going down below like that. But no, remember, this is low tide. That means that this is the smallest value that the function should have ever. That's the least deep that the water ever becomes. It shouldn't go below this point, and it shouldn't go above that point. So if you were to continue to draw the graph, it would probably look something like this, okay? And hopefully you can kind of see the trig function which is emerging. So what we have to do now is write a function which describes this graph, right, which models this graph. And as we've mentioned before, in order to write down a formula for a function, you have to sort of make a choice about what cycle of the graph you're going to use. Where does your cycle begin, right? When we first learned this, I always highlighted cycles for you, but now it's up to you to choose what cycle you want to use. So you could say that your cycle begins here. That's certainly a reasonable choice. I think that's the most natural choice. In which case, your full cycle would be this, wouldn't it? That would be one full cycle. I suppose you could start your cycle here and then say that your cycle looks like this. It's this entire thing. But I think the most natural choice is to say that this point here is the beginning of your cycle. So let's say that that point there is the beginning of my cycle, and construct the formula of the function, the formula of the graph, with that assumption in mind. So first of all, if this is the beginning of the cycle, then certainly this should be a cosine function because the graph begins at the top. So I'm going to recall my generalized cosine function, a cosine omega. I would normally write x minus b, but because my independent variable represents time, I think it makes sense to call it t rather than x. So t minus b plus m. So that's my generalized cosine function. Now, I have to figure out all of these parameters. Well, for one thing, I think the midline can be found pretty easily. The midline would be halfway in between these two values, which can be obtained by taking their average. Halfway between 5.2 and 2, if you take 5.2 and you add 2 and then divide by 2, that will be that halfway point. So that's going to be 7.2 over 2, which is actually 3.6. Okay, so that is the midline, 3.6. Next, we can find, I think, the amplitude, which will give us A. So what is the amplitude? Well, it's this distance right here, right? Or if you prefer, this distance right here. They're the same. So what is that distance? Well, from 3.6 to 5.2, I think that's a distance of 1.6. So the amplitude certainly is 1.6, but remember that A could be 1.6 or negative 1.6. How do we know which one it is? Well, it depends upon whether our cycle is upside down when compared with the parent cosine function. The parent cosine function, you'll remember, begins at the top, just like our cycle, which means this is not upside down, which means that A should in fact be positive 1.6. So we know that A is 1.6, and we've also already observed that M, the midline, is 3.6. Great. What else do we need? Well, we need B, which is the beginning of our cycle. And that brings up kind of an interesting fact. Obviously, our cycle begins at 4:15 a.m., but 4:15 a.m. is not exactly a numerical input, right? I think that if you look carefully at the problem, it says T is supposed to represent the number of hours after midnight, okay? So if T represents the number of hours after midnight, then we have to ask ourselves, what value of T is associated with 4:15 a.m.? Is it simply 4.15? The answer is no, right? I mean, 4:15 a.m. is not 4.15 hours after midnight. What it actually is the following. So 4:15 a.m. 4:15 a.m. is really associated with 4 hours and 15 out of 60 minutes. That's what it is as hours, which 15 out of 60 is 0.25. It's a quarter. So this is 4.25 hours. So the t value associated with this time is 4.25. Okay. All right, so you can see that our cycle begins at t equals 4.25. So we know that B is 4.25. Cool. All that remains is omega, which is the angular frequency, which of course we have to find by determining the period, the length of the full cycle. Well, how long is our cycle? One thing that you have to notice is that the distance from here to here, that's not the period, because from here to here is not a full cycle. From here to here would be a full cycle, which means that this distance, whatever it is only half a cycle. So we're going to have to find this distance and then double it in order to find the period. Of course, to find this distance, we have to convert 1027 to time, or to hours, like we did a moment ago. So what is 1027 as hours? So 1027 a.m. is really associated with 10 hours and 27 out of 60 minutes. So that's what it is written as hours. Now, 27 out of 60 happens to be 0.45. So that's 10.45. Okay, so that's the t-value associated with 1027. Okay, great. So now we're prepared to find this distance here. So how do we find that distance? Well, we just subtract, right? 10.45 minus 4.25 will give me 6.2. So that's the distance from this point to this point, but as we already observed, that's not the period. The period is twice that. Therefore, the period is going to be 2 times 6.2, which is 12.4. So that's the period, which we can then use to find omega. I feel like I'm really running out of room here on this sheet of paper. Not my best organizational work. So the period, as always, is given by 2 pi over omega. So we just observed that the period is 12.4. So we can now solve this equation for omega. Cross multiply, however you prefer to solve this. Okay. Divide by 12.4, you find that omega is 2 pi over 12.4. So that's omega. However, this expression is pretty offensive because it's a fraction which has a decimal. You shouldn't have both fractions and decimals. You should have like one or the other. There's no need to have both. What I'd like to do is get rid of this decimal. And one way of doing it is to multiply top and bottom by 10. Because what that will do is it will move the decimal point here to the right one, and we'll have no more decimals. So we then obtain 20 pi over 124, which, that fraction can be reduced to, let's see, I think top and bottom are divisible by 4. So that's 5 pi over 124 divided by 4 would be 31. Is that right? Yeah. So 5 pi over 31, and that's reduced. So that's our simplified omega. So now we're ready to actually write down the function which describes this graph and which models the depth of the water. So I have y is equal to a, which we said was 1.6, so 1.6 cosine omega, which we said was 5 pi over 31, and then t minus b, we said that b is 4.25, and then plus m, which we said was 3.6. So that is the function which models this behavior. Cool. So now we can now use this model to answer the second part. The second part is find the depth of the water at 1 o'clock p.m. Now this function is able to produce the depth of the water at any time t. All you have to do is plug in the appropriate value for t, and what will pop out is the depth. Now, as always, 1 p.m. is not exactly something that we can plug in. We have to convert that to some value of t. Now remember that t represents the number of hours past midnight. Midnight, that's 12 a.m., which means that 1 p.m. does not correspond to t equals 1. Rather, it corresponds to t equals 13, right? 13 hours after midnight. So all I have to do is plug 13 into this function. So the depth at 1 p.m. will be given by 1.6 cosine 5 pi over 31, 13 minus 4.25 plus 3.6. So whatever this expression winds up being, that's the depth. But it has to be simplified. One quick note, I noticed that a lot of students were kind of confused about exactly how to evaluate this expression. I want to be clear, like, what role exactly does this 5 pi over 31 play? We typically don't draw this. It's kind of unnecessary. But the order of operations, the way in which you should simplify this expression, I think is made more clear if you draw brackets around this expression here. Okay? So really what is happening is you take, first of all, it's the cosine of this entire expression in the brackets, right? You take 13 minus 4.25, and then you multiply that expression by 5 pi over 31, and you take the cosine of that resulting expression. Then you multiply by 1.6, then you add the 3.6 at the end. Without the brackets, it's somewhat less clear exactly what you're supposed to do. I think it makes the simplification a bit more clear. So let's have a look at what this is. So I should make sure my calculator is in radians because I'm using 2 pi for the period. This whole thing is measured in radians. If I wanted to do it in degrees, I suppose it would be 360 over omega. But all right, so yeah, I'm in radians. Okay, great. So let's see. So I'm going to start by figuring out what the expression is inside the parentheses first. So I'll take 13 minus 4.25. Okay, that's 8.75. Cool. Now I need to multiply that by 5 pi over 31. So times 5 pi over 31. Okay, so I get 4.4 blah, blah, blah. Let me just sort of summarize that result. So what I'm looking at is 1.6 cosine of 4.4336, whatever that number is I had here. Okay. Right. Plus 3.6. Okay, so now it's pretty straightforward. We have to take the cosine of that result. So cosine of 4.4336, 99, blah, 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 right? Enter. I get this value right here. That's negative 0.27. So what do I do then? So this expression right here, that whole thing is my negative 0.27 value there. So what I need to do now is multiply by 1.6. So times 1.6. I get this value right here. And then finally I have to add the 3.6. So plus 3.6, 3.159. Okay, that sounds all right. So I have y is equal to 3.1598, blah, blah, blah. And I guess that's measured in meters, right? So the depth of the water at 1 p.m. is 3.159 meters. Okay, that's the idea. All right, so that's basically it. I just want to make a couple of comments. I want to go to some of the book exercises. And the book, regrettably, has some pretty confusing problems. But they are sort of a good learning opportunity, and I want to address them. I don't want to do the problems all the way out, but I just want to make a few comments. First of all, this very first problem, this Bay of Fundy problem, got this cute little picture of the boats. It says the Bay of Fundy, blah, 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 blah. Okay, look, it's a tide problem. Very similar to the one we just did. It's 2 feet at low tide. It's 58 feet at high tide. Okay, and they tell you that high tide occurs 6 hours and 12 minutes after low tide. And they want you to draw a graph of the depth of the water and blah, 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 blah. Okay. So here's what we should say to ourselves. Probably most people are going to say this. They're going to say, okay, you've got the water is 2 feet at low tide. All right? So I'm going to make, sort of a graph here. Right? So 2 feet at low tide. Notice that they don't tell you the time at which low tide occurs. Like, they don't tell you that it occurs at 3 p.m. or 4 p.m. They just say it occurs. And then 6 hours and 12 minutes later, high tide occurs. That's all they tell you. Okay, now this kind of gives you some ambiguity in the graph, or so it would seem. Because possibly, maybe it makes sense to start the graph at low tide. Okay, so here's 2 feet, right? And I've got my dot right there. That's low tide. And then 6 hours and 12 minutes later, you've got high tide, which occurs at 58 feet. So maybe 58 is up here, and we'll just say that, this distance here, I guess if this is 0, then this must be 6 hours and 12 minutes later, okay? And I suppose the graph looks like this, you know, and then you can sort of imagine that it keeps going forward and so on. But here's the thing. We actually made an arbitrary choice here. Okay, we made a choice, essentially, about what t represents. And if you've done a lot of physics, then this kind of question will be very familiar to you. You have to make a choice about what t represents. By drawing this picture, I have decided, somewhat arbitrarily, that t represents the number of hours past low tide. Because think about it. When t is equal to 0, we're at low tide, right? When t is equal to 1, we're 1 hour after low tide. When t is equal to 6 hours and 12 minutes, we're 6 hours and 12 minutes after low tide, right? I guess this, if you converted it, would be 6 and 12/60ths, whatever that number is. But the point is that having drawn the graph this way, I've made an arbitrary choice. The t represents the number of hours past low tide. Now, that's not the only choice that you could make. You could just as well decide, arbitrarily, that actually t represents the number of hours past high tide. Why not? Then high tide occurs right here, that's 58, and then low tide occurs here, and that's 2. And what this tells us is that, you know, I suppose, if you like, maybe some students I think get confused because they're like, well, doesn't low tide have to occur before the high tide? And wouldn't that put you in negative time? And doesn't that not make sense? I think negative time is actually okay here, but like to say that low tide occurs 6 hours and 12 minutes before high tide is not like really the whole story. I mean, low tide occurs before high tide. Low tide also occurs after high tide. It's a periodic phenomenon. Low tide, high tide, low tide, high tide. Okay, so any way you want to think of it, low tide is going to occur after high tide, no matter how you think of it. Now, you could also choose to draw the graph this way. Okay? And what this is doing is it's making a different choice about what t represents. In this situation, t represents the number of hours past high tide, because at t equals 0, you're looking at 0 hours past high tide. In other words, you're looking at high tide. And then when t is equal to 6 and 12 out of 60, you know, you're looking at the number of hours past high tide. So basically what's happening is you're sort of having to choose a coordinate system, okay? And the choice of coordinate system is actually quite arbitrary. If you remember from physics, look, suppose that you're trying to describe in the plane the trajectory of some object. So let's say that these are your xy axes, and you've got some object traveling around, and maybe it goes like this, okay? Now, if you've placed your origin here, then you would say that when the object is right here at this point, its coordinates are, I don't know, maybe that's -3, 2, okay? But the choice of coordinate system, where you put your origin, has no physical meaning. The origin is not something that exists in reality, but rather just something that we impose in order to be able to represent things with coordinates. You could just as easily place your origin here. Wherever you put your origin, the particle's still here at this time in space. And the coordinates that you represent that particle with depend upon where you place your origin. If you place your origin here, then the coordinates of this particle at this time would be not -3, 2, but, you know, if this is your origin, then, I don't know, maybe that's 4, and maybe this is like -5 or something, and so the coordinates would be 4, -5. It's a very similar situation here. You're sort of changing coordinates, deciding what t represents. And it's an arbitrary choice, okay? And sometimes you just have to make that choice and decide for yourself what t represents. Whatever choice you make, you should be really clear and consistent about what t represents. Number of hours past some fixed point in time, so that you're never confused. Now, it may seem that this choice is up to you, that you can just make t represent whatever you want. You could even maybe decide that t represents the number of hours past the midway point, right? And then decide to put your y-axis here. But actually, if you read the problem carefully, they tell you that they want one of these pictures and not the other. So let's look again at the question. It says, draw a graph showing the depth of water at the dock as a function of the time since high tide occurs. Since high tide occurs. That's telling you that t represents the number of hours past high tide. That means they want this picture, not this one. Okay, this is the diagram corresponding to t being the number of hours past high tide. Okay, so watch out for that slight ambiguity. The other thing that I want to mention is sort of just an annoying feature of these problems. Let's jump ahead to number 21. Okay, so let's look at 21. I'm not going to do the whole problem or even really read it. I just want to draw your attention to this graph. What they have is a collection of points, okay? And you can see that the horizontal axis represents day of the year. This is modeling some phenomenon. I think it's the time of sunsets over the course of the year. So when does the sunset occur during different times of the year? Now, you're going to try to write a function for this graph. And at some point, you're going to have to figure out the period. Well, in order to do that, you're going to have to look at how long the cycle is. Now, you may look at this graph and say, well, it sure looks as though the beginning point is 0, and then the graph sort of ends at 356. So I suppose that my period is 356. But that's not really true. This just happens to be the last point of data that they collected for this problem. It doesn't mean that the phenomenon you're modeling actually repeats every 356 days. Okay, maybe suppose they got lazy and stopped collecting data here at this point. Does that mean that this should be a full cycle of the graph? No. This is representing something which happens over the course of a year. The period of the function should be 1 year. It should be 365, okay, regardless of what happens to be the last data point. So don't make the mistake of thinking that the period should be 356. It's 365. And if you look at the answers at the back of the book for this thing, you'll see that their omega value is like 2 pi over, it's 365 over 2 pi or something like that. Whatever it is, it's involving 365. The omega value they choose corresponds to the assumption that the period is 365. That's all well and good. And I like the fact that you have to think about what the period should be here. And I like the fact that you should have to think to yourself, should the period be 356 or should it be a full year? But, so, number 17, though, if you take a look at this graph, once again, you're going to have to figure out the period. And looking at this graph, it sure looks like the cycle begins at 0. And with them highlighting this dot here, it sure looks like it ends at 355. Very tempting to say, oh, the period is 355. Very reasonable. But if you look at the answer at the back of the book, the omega value they have is what you would get if you assumed the period was 365. Okay, look, I understand that sort of logically, since this problem is about a phenomenon which is taking place over the course of a year, I understand that logically it makes sense that the period should be an entire year, should be 365, but the graph definitely doesn't look that way. I think what's happening technically is that it's hard to tell because the graph is kind of zoomed out, but I think actually this point here is not actually the bottom of the curve. It's not quite. I think the graph actually, forgive me for writing in the textbook, I think the graph actually continues a little bit below, okay? And that the bottom of the curve appears like there. And that this point here is actually not the bottom of the curve either. It's like slightly to the left of it or something. Okay? So basically, logic tells you the period should be 365, but the graph is extremely deceptive and seems to suggest that it should be 355. In this exercise, you should assume that the period is 365. That's what the book assumes. But rest assured, I will not give you any such deceptive and misleading pictures on an assessment. Okay, so I hope that clears things up.